Hello and welcome. Let's dive into another concept of shear force and bend moment, and which is point of contraflexure. And what do you mean by contraflexure? Point of contraflexure is the point where bending moment is equals to 0 after it changes its sign from positive to negative or from negative to positive. That is, on our bending moment diagram, we are going to have a point where our bending moment start changing its sign. It's either a change from positive to negative or from negative to positive. At that point is the point of what? Contraflexure. So we are going to take this as an example. All right, so the first thing we are going to do is we are going to take the summation of forces. Upward force to be equals to what? Downward forces. That is, the sum of forces in our y direction should be equals to 0. So after that, we take our coordinates. That is, upward force will be positive and downward force should be what? Negative. All right. So now we are going to have our reaction at A plus reaction at B to be equals to. Now we are going to convert this uniform distributed load to a what? To a point load. And how do we do that? For us to convert a uniform distributed load to a point load, we are going to note the point that it covers on our beam. It covers from A to what? To C. So the total distance is going to be 2 plus 4, which is what? 6. So we are going to multiply the weight of the uniform distributed load by the total distance. So it's going to be 2 multiplied by what? By what? By 6. So now which is going to be reaction at A plus reaction at B to be equals to what? To be equals to 12. Let's call this equation number 1. So the next thing we are going to do is we are going to take our moment. We are going to be taking moment about point what? Point A. So the summation of moment about point A will be equals to what? 0. All right. Now, so about this point, we are going to have 0. So here we are going to have RB. Don't forget, we have already said upward force should be positive. It means our upward force here is going to give us a what? An anti-clockwise moment. So it means anti-clockwise moment is what? Is positive. So we are going to have RB multiplied by what? 4. So RB multiplied by 4. All right. So here we have our uniform distributed load, which has been converted to a point load. And when we do that, it is nothing but what? But 12, right? So that is 2 multiplied by total distance, which is what? 12. Don't forget, it's going to be minus 12. All right. Now, what distance is it acting? Don't forget, anytime you convert a uniform distributed load to a point load, it's going to act at what? At the half of the distance that it covers. That is at the center. Exactly. All right. So it's going to be what? The total distance here is what? Is 6. So it's going to be multiplied by what? It's going to be multiplied by 6 divided by what? 2. That is, the total distance is 6. So 6 divided by 2 to what? To the point A. All right. So everything will be equals to what? To 0. All right. So here we are going to have 4 RB. All right. So here we are going to have 2 here 1, 2 here 3. 12 times 3 is what? Is 36, which is equals to what? 0. So if we move 36 to the other side, we are going to have 4 RB to be equals to 36. So for us to get RB, we divide by what? By 4. So RB now will be equals to what? 9 kilonewton. All right. So for us to get our reaction at A, we are going to substitute 9 for what? Equation number 1. So we are going to have our RA to be equals to 12 minus RB. That is 12 minus 9, which is what? 3. That is 3 kilonewton. All right. So the next thing we are going to be doing is we are going to be starting with the shear force calculation. All right, so we are going to be starting with the shear force. Now, let's start with the shear force at point C. All right, the shear force at point C. At point C, we don't have any force at point C. So it's true that, you know, our shear force, we can calculate that to the left or to the what? To the right. So I normally calculate my own to the what? To the right. So now this is it. If you stand there, we don't have any force. So that the shear force at point C is what? 0. All right. So the next point here is the shear force at point B. All right. So at point B, if we stand at point B, what do we have? We have a uniform distributed load there. So if we convert this uniform distributed load to a point load, is going to be 2 multiplied by what? By 2. So it's going to be 2 times 2, which is 4. But don't forget, it's going to be acting as a what? As a downward force. So it's going to be minus 4. So it's going to be minus 2 times 2. All right. So now, and don't forget again, at point B again, we are having an upward force. That is the reaction at B, which is going to be what? Which is going to be, reaction at B is going to be what? 9. So if you do this, minus 2 is minus 4. That is minus 4 plus 9, which is going to give us what? 5. The meaning of this is at point B, we are having 2 shear force. The first one is the what? Uniform distributed load. And when you convert that to what? To a point load, you are going to have negative 4. All right. So now, by the time you now add the effect of this reaction at B to it, is going to change from what? Negative 4 to what? To 5. That is the meaning of that. All right. So now let's go for our shear force at point A. The shear force at point A will be equals to, all right. Now, we start at point A here. We are going to have a uniform distributed load, right? So which is 2 kilonewton per meter, right? So if we convert that to a point load, it's going to be negative 2 multiplied by total distance, which is 6. So we are going to have negative 2 multiplied by 6. All right. So now again, if we stand at this point again, we are having a downward force here, which is what? Which is ROB. So and our ROB is what? Is 9. So which is going to be what? Positive, because upward force is positive. So it's going to be 9. So this is going to be equals to minus 2 times 6, that is minus 12 plus 9. So minus 12 plus 9, that is minus 3. So it's going to be minus 3 kilonewton. All right. So here, please, your unit is kilonewton. All right. So now, the next thing we are going to do is our bending moment calculation. All right, so we are going to start with the bend moment at point C. Of course, at point C, we don't have any force, and there's no distance to the what? To the right. So this is going to be 0. All right. So now the next one is going to be the bending moment at point B. All right. So bending moment at point B. Of course, if we start at point B, and then if we move to this side, we are going to have a uniform distributed load. If we convert that to a point load, that is 2 times 2, that is 4, right? And don't forget, it's going to be a what? A downward force. And a downward force is what? Negative. So it's going to be minus 2 times 2. Then the distance that is going to cover, don't forget, it's going to cover half of the total distance here. That is, we're going to have minus 2 times 2. So this here is the uniform distributed load converted to a point load. All right, so the distance it covers is what? Is 2. So it's going to be times 2 divided by what? By 2, because it's going to act at what? Half of the what? The distance. So here we are going to have minus 2 times 2 is minus 4 times 1, that is minus 4 kilonewton meter, because we know that moment is force times perpendicular distance. So the last but not the least, which is the bend moment at point A. All right, bending moment at point A. If we stand at point A here, we have a uniformly distributed load, which is 2, or you can start with ROB times 4. That is, and our ROB is what? Our ROB is 9. So it's going to be 9 times 4. All right. So now, if we stand here again, we have another uniform distributed load, which is 2. And if we are trying to convert to a point load, it's going to be a downward force. So 2 times total distance is what? Is 12. So here we are going to have minus 2 times 6. All right. And the total distance now is going to add. Now it's going to be 6 divided by 2, because the total distance from here to here is 6. Divided by 2, you get the distance that is acting. All right. So 9 times 4 is 36. So, and here we are going to have 2 here 1, 2 here 3. And 2 times 6 is 18. 18 times 3 is 36. So sorry, 2 times 6 is 12. 12 times 3 is 36. 9 times 4, 2 is 36. 36 minus 36 is 0. So we are going to have 0 here. All right. So now we are going to be using this information to draw our shear force and bending moment at diagram. So for us to do that, we are going to draw a straight line down everywhere that we have what? Everywhere that we have load. So we are going to do that now. All right, so here is we want to draw the shear force and the bend moment diagram. So we are going to need a reference line. We are going to start with our shear force diagram. Here is our reference line for our shear force diagram. Above this line is positive, below is what? Negative. This is the reference line for our bend moment diagram. Above is positive, below is what? Negative. All right, so now the shear force at point C is what? 0. Here is our 0. All right, so that is 0. Now, the shear force at point B is 5, positive 5. So let's take this point as our positive 5. This is B. So let's take this point. Let's take that point as our 5. Sorry, before then. Oh, sorry. Now, I said the other time that we have two shear force at point B. The first one is what? -4. Please don't make such mistake. We have -4. All right. So let's make this point our -4. Let's make this point -4. All right. So let's make this point -4. So from this 4 now, when I now add the effect of this reaction at point B there, it now change from -4 to what? To 5. So let's call this place our 5. All right. All right, so we are going to be joining this point because we have a uniform distributed load on the beam. So we'll be using an inclined line. All right, so that's it. All right, so for this one too, we are going to be using an inclined line. All right. All right. All right, so and at point C now, sorry, at point A, our shear force at point A is what? -3. All right, so from this point now, here we have here to be -4. So it means -3 should be somewhere around here. So that is -3. So we are going to use an inclined line to join this point with this point. So I would like to change it. All right. So we are going to join this point with this point. All right. So that's it. All right. So that's it. So we are done with our shear force diagram. All right. So you can therefore shade now. And shade. All right. So that is our shear force diagram. All right, so let's go for our bending moment diagram now. All right, so our bending moment diagram at point C is what? 0. So here is 0. All right, and at point B we have -4. So here we have -4. So let's make this place to be our -4. All right, so and at point A we have 0. At point A we have 0. All right, so our bending moment at point C is 0, bending moment at point B is -4, and bending moment at point A is 0. All right, so for us to draw the bending moment diagram, we are going to be looking for the point where we are going to have our maximum bending moment. Now, and we know that our shear force crosses this line at this point here. It means our shear force is equals to 0, and anywhere we have our shear force to be equals to 0, we are going to have maximum bending moment at that point. So I'll be drawing a line. I'll be drawing a line here. All right. So at this point, we are going to have our shear force to be equals to 0. So the distance, let's name this from this point to this point to be y. So if this point to this point is y, now we can calculate our shear force about this point now. So for us to do that, we know here we are having arrow A and a uniform distributed load here. So here we are going to have it to be arrow A, at this reaction at A. Then this uniform distributed load, which is the weight is 2. We are going to convert it to a what? To a point load. So for us to do that, we are going to multiply the weight by the total distance, which is what? Y. So, and don't forget, we have named our coordinate upward force positive, downward force negative. That is why our arrow A there is what? Positive. So now it's going to be minus 2 multiplied by y, which is what? 2y. Then we are going to equate this to be equals to what? 0. Don't forget that our reaction at A is nothing but what? 3. So we are going to have this to be 3 minus 2y to be equals to 0. So 3 will be equals to 2y. So for us to get the value of y, we divide both sides by 2. So the value of our y now will be equals to what? 1.5 meter. So it means that our shear force, it is 1.5 away from point A. Do you understand? That is where our bending moment will be equals to what? 0. All right. So now for us to get the point where our bending moment is equals to 0 now we can find our moment too about this point. Now we can find our moment about this point. So for us to do that, we are going to say B max, that is maximum bending moment, will be equals to, now the bending moment about this point now, arrow A multiplied by total distance, that is arrow A multiplied by y. You understand? And then we know that our arrow A is what? Our arrow A is 3. So it's going to be 3 multiplied by what? By the distance, which is what? 1.5. That is our y. Then again, we have a downward force here. Our downward force here is nothing but what? It's nothing but if we convert this uniform distributed load to a point load, we are going to have it to be what? 2 multiplied by y. That is minus 2y. That is 2 multiplied by 1.5. Then times 1.5 divided by 2. All right. So if you do all of this stuff, I hope you understand that, because we take our moment about this point, it's going to be arrow A multiplied by what? The distance. Do you understand? And here again, we have a uniform distributed load here. If we convert to a point load, it's going to be 2 multiplied by y. Then it's going to act at where? Half of the distance. That is why it is what? That is why it is 2 multiplied by 1.5, because our y there, we have calculated it to be what? 1.5. All right. So now if you press 3 multiplied by 1.5 minus 2 multiplied by this, you are going to have 2.25. 2.25. Then don't forget, the unit for our bending moment is what? Is going to be what? Kilonewton meter. So that is where we are going to have our maximum bending moment. So it means that this point now, don't forget, here is 0, here is -4, here is 0, and above this line is positive. So it shows that we can trace our 2.25 somewhere here. Let's make this at this point. So here is our 2.25. So now it means that our diagram now, the bending moment diagram now, is going to look like this. All right. Please. All right. So here we are going to have something like that. So here we are going to have something like this. All right. So that's it. So now we can therefore shade now. All right. So here is positive. Here is positive. Let's just clean this point. Positive. And here is negative. Here is negative. Here is positive. Here is negative. All right. Now we are done with the bending moment and shear force diagram. So now we want to look at the point of contraflexure. Don't forget, I told us earlier before that the point of contraflexure is the point where our bending moment is equals to 0 as it changes its sign from positive to what? To negative. All right. Now, if you look at this now, this is our bending moment. From this point to this point, we are having everything here to be what? Positive. To be, sorry, I made a mistake. All right. This is negative. Sorry. This is negative, while this is positive. All right. So now we are having everything that we have here. This is our point B. It's changing from this point from negative to what? To positive. At this point, everything here is negative up to this point. Then it changes to what? To positive. So here we are going to have a point of contraflexure. So our point of contraflexure is going to be at this point. So this is our point of contraflexure. All right. So now, how do we get? How do we calculate the distance? How do we calculate that? So I'm going to draw a straight line here. All right. So let's just put an arrow here. So let's write points of contraflexure here. All right. So here's our point of contraflexure. All right. So now we can name from this point. Now we can either calculate our bending moment either to the left or to the what? To the right. So now from this point to this point, let's name it to be our what? Our x. So let's name this point to be our x. All right. So now if we want to calculate our bending moment now, so it's going to be what? So the point of contraflexure. So let's say point of contraflexure. So let's just use PC of contraflexure will be equals to, it's going to be equals to the moment now. It's going to be RA multiplied by what? By S. So it's going to be RA multiplied by S. And our RA is what? Our RA is 3. So it's going to be 3S. Alright. Now don't forget, we are having a uniform distributed load here, which we are going to convert to a point load. The weight is 2. So it's going to be 2 multiplied by total distance, which is what? Which is S. Right? So we are going to have S here. So it's going to be minus 2S, then multiply by what? Multiply by the it's going to cover half of the distance there. So we are going to have x all over what? X all over 2. All right. So now don't forget that we are looking for the point of contraflexure, and we said the point of contraflexure is the point where our bending moment is equals to what? 0. So if we equate this equation to be equals to 0, what are we going to have? All right. So we are going to have, don't forget, these two will go with these two. Then we are going to be having 3s minus s squared. That is 3s minus s squared to be equals to what? 0. All right. So from there, if I factor out s is common, if I factor out s, I'm going to have s into 3 minus s, which will be equals to 0. All right. So it means that from the zero law from quadratic, it means that either s is equals to 0 or s is equals to what? You move this to the other side, it means or s is equals to what? 3. So which of the following value is visible? Of course, our s cannot be 0, it must be what? 3. So it shows that the point of contraflexure is 3 away from what? Point what? From point A. Because we take our bending moment towards this side. Is either you take it towards this side or you take it towards this side. And you might want to ask, what will be the distance from this point to this point? The distance from this point to this point is going to be 4 minus what? Minus s. Because from here to here is 4. And from here to here is s. So here is going to be 4 minus s. Alright. So it means that our point of contraflexure is nothing but what? Is nothing but 3. is at a distance of 3 from point what? From point A. So that will be the solution to this question. I believe you understand this perfectly. So you can let us know that in the comment section. Thanks.